Welcome everyone. So this is our 114th live stream geometry. We have two people here with us now, Stefan, Sebes, and Georgie. And today we are going to go through problems from the Korea Math Olympiad from a bunch of different years. And we're also going to do one problem from the recent Serbia team selection test. So I want to congratulate Stefan. He's on the session for qualifying for the IMO. So let's all wish him good luck. And if you want to join us in the future, feel free to email me at mgreenv801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. So here is the first problem, which was taken from the Serbia team selection test. So Stefan, I think, probably already knows the solution. So me and Georgie will work on it for the time being. So we have a triangle ABC. And if we really get stuck, Stefan can give us some hints. So we have a circle centered at A, and it intersects the two sides at E and F. So it intersects AC at E and AB at F. And then we also see where it intersects the circle of ABC. So it intersects it at X and Y. That's X, and this is Y. All right. And B is on BC, so that AD, BE, and CF concur. So we could use Chepa's theorem because of that. We might be able to use projective geometry and harmonic conjugates. And it looks like coffee is joining. All right, let's call this something else. We call it, I don't know, Z, why not? Hey, Coffee, thanks for joining us. And this point is D. All right. P is where XE and YF intersect. And Q is where XF and YE intersect. So this is P. And then this would be Q. I wonder what happens if like Q is the midpoint of BC, if this ends up this circle, well, the circle can't pass through A because it's centered at A. So, all right. I wonder if it's worth like making these lines intersect the circle, but for now I'm just going to draw it as segments. We want to show the perpendicular from D to EF lies on PQ. Okay, so it is kind of like a generalization of the Sharpie double, possibly. So let's see. If, yeah, so if E and F are the tangency points of the incircle, then maybe it reduces to the Sharpie double. That's what it seems like would probably be the case. Okay. And there's many different ways to prove the Sharpie double. Like I would say the simplest is inversion about the incircle, but we don't have an incircle here. So maybe inversion about circle centered at A. Although, let's see. So let me drop a perpendicular from B to EF. And that'll be G. So we want to show that P, G, and Q are collinear. I don't think Z lies on it, but let's check. Maybe it does. No, it doesn't look like it in this picture. Yeah. Okay. There's a couple different ways. So, like another way to prove the Sharkey double is that like GD is an angle bisector. So okay, so I think that might be a better way to go. So we let EF meet BC at a point, and then we get some harmonic conjugates because this is a right angle. No, I'm sorry, this is a right angle. But are these equal? Yes, because this is isosceles. So this angle equals this. Actually, I'm not sure if that's true. Let me check. Is this an angle bisector? Yes. Now why is that true? Because we know angle BFG is GEC. It's like Leia is joining. So, hey Leia, thanks for joining. Oh, she's still connecting. Hey Leia, thanks for joining us. So this is our first problem. This was on the team selection test that just happened from Serbia, and Stefan took it and he qualified for the IMO. So that is the good news. So he probably already knows the solution to this, but I'm just working through it right now. So let me see why it's obvious that this is an angle bisector, or if it is obvious.
It's obvious from Roman loss configuration.
It's obvious through what?
By harmonic bonded HGBC.
Hold on one sec.
Because ADBEC. Okay.
Okay, since these three concur, then we know these are harmonic.
Yes, by
oh, okay. It follows from the fact that. Wait. So, sorry. So it's the same as saying HBDC is harmonic, right?
Yes, and it is true because ADBEC. Okay.
Oh yeah. So it's obvious because since those concur, HBDC is harmonic, so this has to be an angle bisector. And then that means these two triangles are similar, FGB and GEC. So that's going to give us some useful ratios. So then we have FG over GE is FB over EC. And okay. And is there any spiral similarity that we have here? So we know FGB and EGC are similar. 1 second, I'll be right back. Sorry. Yeah. I am back. So yeah, thanks for waiting. Okay, so we have similar triangles. Maybe, I don't know if Sargs or Pascals or Pappas could show these are linear. We have XF and YE, XE and YF. And if we draw
Okay, take the intersection of XY with EF.
the tangents at X and Y, right? Are those collinear with P and Q, the intersection of those?
Intersection of XY with EF
Okay, but
is also true.
okay, sorry. So I think by Pascal's theorem, P, Q, and I would be collinear. Right? I could call this something else instead of I. Let's call it I don't know, V. But if V is the antipode of A, so it's where the tangents meet, then P, Q, and V are collinear. So really we just have to show that but yeah, I wonder what this. Yeah, I'm gonna draw V. Sorry, was this what you were saying, Coffee? I couldn't hear you that well.
Intersection of XY and EF.
The tangents at X or at X and Y?
XY and EF.
Oh, X, Y, and EF. Okay. So this one right here?
Yes.
All right.
And we want to show G lies in the polar of I.
Okay. You want to show
Card.
G lies on the polar of I.
Yes.
And since this is perpendicular, okay, so let me use the pull and polar tool. Oh yeah, okay. Because yeah, by Ricard's theorem, PQ is the polar. Interesting. Okay. And that's of course the same as showing that the cross ratio IFGE is 1. We know HBDC is 1. Oh, so you know what? We know that FG over GE is BD over DC. And we know that this cross ratio is 1. So if we want to show that this cross ratio is 1, that's like the same as showing that IF over FE is HB over BC. Right?
Yes. So we have to show BI is parallel to.
We have to show BI is parallel to what? To this?
SC maybe.
Okay. Okay, it's not parallel to that. Sorry, what is BI parallel to?
BI parallel to SC, maybe. No, sorry.
All right. You need to show IF over IE is HB over HC. Yes, exactly. That would show that, because if that's true, then that would mean these are harmonic, which would mean G lies on the polar of I. and then by Ricard's theorem, that polar is PQ. So yeah, I could maybe get rid of V. I'll just leave it there for now. So, okay. So let's think about that. How would we prove that? IF over IE and HB over HC. I wonder if X and Y, I wonder if this angle equals this angle. I don't think it does. But I'll check it just in case. Oh, it does. Interesting. So really, it's like this line and this line are like corresponding lines in the same figure then. That's surprising to me. Why is that true? I don't know if that's obvious. Or if that's just like an angle chase. Might just be an angle chase. So this angle, it's half the difference between arc YE and FX, which is basically, is it just the difference between this angle and this angle? Might be. Yeah, because it's this minus that, which is this minus that. Okay, so then this angle here, like I don't know if we want to draw this whole line and see where it meets the circle. So let me just delete these two. I know we have to prove those are the same. We have this and this. And we're trying to show like the whole figures are similar. So let's see. Let me draw the center. This O. Yeah, but these circles don't correspond to each other in the similarity because OBC is twice FAE. But if we take the midpoint of arc BAC, there's a couple ways we can think about this. So I'm going to draw the midpoint of arc BAC. That would be this point up here. Called M. And I think MBC is similar to AFE. So basically that means that like we're trying to show like similar figures. So here we have MBC is similar to AFE, And we want to show HB over HC is IF over IE. So basically we want to show, like, really it's like I would want to draw, what would happen if I drew that circle, this circle? That would like correspond to that circle. I don't know where I'm going with this. Maybe I'm making it harder than it needs to be. Let me just delete that. I'm going to delete V for now. Just try to make life easier. So IF over IE is HB over HC. That's the key here. How do we find IF over IE? So IF times IE is the power, and HB times HC is the power. We could try Menelaus, although I don't know. I don't really like that. So HB over HC is BD over DC because, okay, so HB over HC, that's BD over DC because they're harmonic, which is BG over GC. And then these triangles are similar, so that would be FG over GE. So yeah, we're kind of going in circles here. Okay, we have to show, yeah, how do we show IFGE is harmonic? We know it. Can we project? This is tricky. Let's see, what time is it? 9:30. So I like, so we know HB over HC is BD over DC. How do we use that? IF over IE. What do we know about point I? Oh, what?
Right? We haven't used A equals F yet, so we should use that.
We haven't used what?
A equals F.
AE equals AF. So we've kind of used that to show that triangles BFG and CEG are similar.
Oh yes.
So yeah, that could be helpful. I want to project IFG and E through something else. I just don't know what. Like, should I project it through B? Let's see, if those are harmonic, I'm trying to prove in a different way that those are harmonic. So that would be the same. Can we find like 3 concurrent Chebians that prove that it's harmonic? So what if we look at I think it's the same as saying, but yeah, this is kind of going in circles. I was going to say that YFXE and QP concur, or QG concur, but that's just going in a circle. Yeah, point I is kind of hard to use, I feel like. Yeah, I'm trying to find the key to point I. So yeah, we have to use that AX equals AF equals AE equals AY. So that's kind of important. Like we have to use that X and Y. So if we know these 2 angles are equal, does that help at all? Actually, if we know angle YIJ equals angle JHC, I wonder if that just can we use that to find some similar triangles? So I could just try measuring a bunch of angles. That's 52 degrees. This is 43 degrees. It's also going to be 43. And then this is 33. Where can I find similar triangles? Let's try this. No. I wonder what this angle is. $60. This angle 74. And we use, so we want IF over IE. do we try to use the radical axis theorem somehow? Because like, let's see. So we have x, y, and then there's some circle passing through these. Let's see. Maybe the circumcircle of DEF. So it almost looks like the end circle, but of course it doesn't have to be. So I has the same power with respect to all three of these circles. So it has to lie on the radical axis of these two. I just don't know if DEF is the right circle to do. Let's try a different circle. I wonder if IB is, I don't think IB is tangent. What are the tangents from I to the big circle? Let's try that. Doesn't look like anything super special. Whoops. Yeah, I just don't know what to project I through. So we could project it through A, but then we just get some point here, and I wouldn't know too much about that point. Let me see if there's anything special about this point. Maybe I could project it onto this circle. So yeah, let me see what I could project I, F, G, and E through. Is there anything special about this? I don't think so. Yeah, this point I is just unusual. So this reminds me a little of a problem from Peru team selection test. So we know, yeah, the tangents at X and Y meet on the circle. What do we know about I? Oh, do we want to show, we want to show IF over IE is FB over EC. That actually looks not so bad because IF over FB is like, we could look at triangle IFB, and IE over EC, we could look at triangle IEC. So maybe that could work. But oh, and those angles add up to 180. So we want to show that IFB and IEC are like pseudo similar. Oh, but wait a sec. So wait, we have IFB and IEC. When I say pseudo similar, I mean the angles add up to 180. So okay, maybe IFB is similar to ECJ. Could that be? I don't think so, but I don't know. Let me check some angles. So try FBI and JCE. Oh, no, they're not the same. But let me just make sure. So I'm going to also look at this angle. Yeah. So oh no, because it's IF. Yeah, IF over FB is IE over EC. That's what we want to show. So it's kind of like saying, like, if we were to reflect I about F, then it's kind of like saying we want to show I prime FB is similar to IEC. It's one way to think about it, which is the same as saying that this angle equals this angle. So I could check if that's true. 23 degrees, and this should be, whoops, not that one. This. Yes. And then saying that those are equal. Is that the same as saying we have some kind of, so wait. So I have this. So those two meet at A. So basically it's like saying, it's the same as saying that A is the midpoint of this R. A is the midpoint of arc MN. Or it's the same as saying MN is parallel to XY. Let me see. But yeah, I'm kind of breaking the symmetry by reflecting I over F instead of E, so I don't know if that's a good thing. Or if I really need to do that. Let me get rid of I prime. Let me just think about how I would show that ratio. So I try the law of sines. So what do we know about triangle IEC?
There's a way to get rid of IE over IF.
Okay.
There's a theorem which says IE over IF equal Fx into Fy over Ex into Ey.
Oh, really? It's fx over xy over ex over ey?
Yes, something like this.
Okay.
But I don't know how it helps.
Hmm. Let's see, if these are harmonic, then is that the same as saying if we take the midpoint, let's say we take the midpoint of EF? I think that's the same as saying that, what is it, MF squared is MG times MI. We could show that. See what time it is. It's almost 10, so may want to move on to the next problem soon. So yeah, let's work on this for like 10 more minutes at least. I don't really like point I. I just don't know how to use it. Like maybe it's better to redefine the problem, like let PQ intersect EF at G prime, and then we know that those aren't harmonic. So if we knew these were harmonic, what could we do with that? What if I draw a perpendicular from D to BC? Then draw a perpendicular. Let's see, I want to show these are harmonic. They don't have a right angle, that's the issue. Yeah, how do I get a right angle here? I could try to draw the circle with diameter IG. Or I could try to draw the circle with diameter FE. So let's do that. FE. So we have that circle. And then for any point on this circle, we're saying it should make an angle bisector with ING. Maybe this point. That almost looks tangent, but oh, is that actually really tangent? That would be interesting.
It should be tangent if the problem is true.
It can't be. Oh, it should be if the problem is true, is what you're saying.
Yes.
Okay. Well, so PQ is the polar of I with respect to this circle. But then if you look at this circle, yeah, they would have to be true. Yeah. So it's been a little while, Stefan. Do you have any hints for us, or is this how you were thinking about the problem?
I was doing something else, but one hint I would give you is to intersect AI with the circumcircle of ABC.
Okay. All right. So then we have point N. Let's think about that. Is this a no? I doubt this is a right angle. That wouldn't make sense. So N is N collinear. So it looks like N is collinear with those points. So that might be. Sounds like that's kind of what Stefan is thinking. And not only that, it seems like these concur there. Okay. Which is kind of interesting. Why is that? Wait, is this a right angle? Why is that a right angle? What do you think about that? Okay, this this is really interesting. That point N does seem really useful. Why is that right? Well,
Okay, AEF and cyclic. It can help.
oh, I guess if the problem was true, then AXS would be 90. So but I'm sorry, what were you saying?
Draw the circle AEF. The inline on the circle.
AEF what?
AEF and its cyclic.
Okay, so AEFN is cyclic.
By power of point.
Okay. Okay, so we want to show N lies on the polar of I, right? And that's equivalent to saying that AN times AI is like AF squared. So maybe that's just like an angle chase, because I think that's an angle chase. So yeah, inversion might help too, but I think so. So we could show N lies on the polar of I. And then if angle ANG equals 90, then G would lie on the polar of I, so that would solve the problem. So how do we show angle ANG equals 90? Is there some circle like this? Well, that would be the same as saying that NG is the angle bisect. Well, oh, okay. So a spiral similarity, I think, takes NFE to NB to BNC. So I think we're getting close here. So is INF okay, so we have a spiral similarity. Yeah, so we want to show N and G are corresponding points in the spiral similarity. And I guess so NFE is similar to NBC. And so, oh, you know what? I think because ND is the angle bisector. Now I'm just getting confused. So I think HND is HND 90 degrees? I'm just going in circles now in my head. Yes. And that's true because those are harmonic and ND is an angle bisector. Okay. So I think I have this. So angle BND is 90. And sorry, angle HND is 90. And we want to show angle ING is 90. Dang it. I feel like we're close and I'm just getting confused now. Oops, sorry. Oh, are T, N, and H collinear? And is that obvious? That's probably easy to prove. So once we could prove that, maybe the problem is easy. Because then the whole figures would have to be similar. So we have ANIFE and TNHBC. So basically, if we can show that those figures correspond to each other, then that would solve it. So how do we know T, N, and H are collinear? That can't be, it's very hard to show. Okay. So yeah, so how do we know T, N, and H are collinear? I think once we show that, the problem's solved. I think. Is that just like the radical axis theorem somehow? I want to show T, N, and H are collinear.
T, N, and H are collinear, that is obvious.
It's obvious.
Because of the angle bisector thing you proved earlier. NT is just the other angle bisector. And ND is the internal, NT is the external.
Oh, ND is the internal and NT is the external.
Yeah. You already proved that ND is internal.
Yeah. And then these are in harmonic conjugation. So, okay.
Basically, T doesn't help. At least I think so.
Okay. I was thinking, the reason why I was thinking of using T is, so basically I want to show
Yeah, I see you try getting some spiral similarity.
yeah, so. Oh yeah, okay, so it's obvious that these are collinear since ND is an angle bisector. And then basically I'm showing the points T, N, H, B, C correspond to A, N, I, F, E. Is kind of what I'm trying to show. And so if those are all similar figures, oh, and also G corresponds to D, we already proved that. Then since these are in harmonic conjugation, so are these, and now it solved the problem. So yeah, like I don't know if there was an easier way to think about that, but I think that works. So, but then we would just have to show I think we'd have to show angle ANT equals angle THJ, which is probably just an angle chase. So yeah, let's write this out. So I'll delete point S. Let me think about that. So I want to show. Yeah, I have a bunch of ways to do this. I'm just trying to find the easiest way. Yeah, so yeah, maybe I don't need T, but if I don't use T, basically I want to show that KNE is similar to HNC. And maybe that's just obvious by the spiral similarity. Or sorry, INE and HNC. Yeah, so because INE and HNC, INE is 180 minus ANE, and HNC is 180 minus TNC. So we want to show TNC equals ANE, and that's easy to show. Okay, so yeah, I'll just leave point P in there, and then I think I'll write it to proof. So let's see, let AI meet the circle at N. Now this always pops up. It kind of drives me crazy, but I don't know a way to stop it. So let AI meet ABC at N. I'll say let P be the midpoint of arc BAC. Okay, so first we will show that so ANFE is cyclic, and but that should be true by power of a point because IN times IA actually, why is that true?
Yeah, IN times IA equals IE times IF equals X times IY.
IX times IY. Okay. So IN times IA is IX times IY is IE times IF. Okay. do this. ANFE. And then once we have that, so triangle AEF is similar to TBC. That's not hard to show. So since both are isosceles with an equal angle, equal vertex angle, okay. And then we want to show I and H correspond to each other. So, and then showing G and D correspond are hard. So I didn't even define. So let EF meet BC at H. Okay. And we know FG over GE is BD over DC. So, and I'm going to prove that, but really we want to show that I corresponds to H. So to do that, I mean, all we really need to show is angle NAE is angle HTC. Okay, so first we show HN and T are collinear, and that's true because HBDC are harmonic, and by the spiral similarity, we have that those are similar. Okay, so by spiral similarity, NB over NC is NF over NE. Okay, so first, actually, I don't even know if I need point H really. We could just really use the spiral similarity. So, well, actually, I do want point H. Okay, so HBDC are harmonic. So BECF and AB concur. AB concur, and that implies HBDC is harmonic. And that implies, let's see, that would mean that GD bisects EG C. EGC. Okay. And that means that from there we get angle FGB equals angle EGC. And that means that FGB is similar to EGC. Which means FG, but then we have NFB is similar to NEC. So So basically, FG over GE is sorry, now I'm just confused. So FG over GE equals GB over GC equals so ND over NC is equal to it's FB over EC. Which is GB over GC, which is BD over DC. So yeah, maybe there's like a way I can simplify this, but this is what I'm thinking about for now. So that means that ND bisects angle BNC. Actually, I think I made it harder than it needed to be. Like N corresponds to. Actually, I'm not sure. Maybe I didn't. So, and that implies that HN and T are collinear. Since HBDC is -1. Oh, it should be BCDH. That's harmonic. This is harmonic. And then that means I corresponds to H. So basically this means that the figures ANIFGE and TNHBDC are corresponding. So okay, so GE, is that right? ANIFGE corresponds to TNHBDC.
How do we know that?
Because so ANFE is similar to
ENBC.
TNBC. So they have to correspond. And then FG over GE is BD over DC. It's kind of what I was thinking. TNHBDC. And if that's true, then since HBDC are harmonic, IFGE is harmonic. So, FEGI. And that means that G lies on the polar I with respect to AF. With respect to the circle centered at A. So I'll say XYEF. Maybe put that in a new line. And that means that G lies on PQ by Picard's theorem. Like I feel like there has to be an easier way to just present this proof. But yeah, my brain can't think of it right now. So let me put that last statement at the bottom. So what was your way of solving this, Stefan?
I didn't do this spiral similarity.
Okay.
However, I drew in point N.
Okay.
And then I noticed that by this point, we can basically delete X and Y. That is because if you define I as the intersection of AN and EF and G as in the problem, then you just need to prove that I, G, F, E harmonic. So we can then delete X and Y.
Yes.
And here, so the thing I did, which you didn't, is I intersected AG with the circumcircle of ABC.
Okay.
Then by projecting, we just need to prove that N, B, C, and that point are harmonic. So not sure exactly what I did, but I proved that H, S, D, G, N are all cyclic.
Okay.
And with that, I could like prove it that those are harmonic. Actually, because all of them are on a Apollonius circle.
Yeah.
Yeah. So proving those are harmonic is equivalent to proving those are cyclic, because I did exactly the same proof that N and G are on Apollonius circle. So if S were also on the same Apollonius circle, then we would have the ratios which would prove that
it's harmonic. Yeah.
Yeah.
NP over NC is SP over SC. Yeah, that would prove it's harmonic.
And I think I proved that S, D, and T are collinear.
Okay.
Well, that is obviously like needed to prove,
Yeah.
but yeah, something like that.
And that, well, so SD and T are collinear is equivalent to showing FG over GE is BD over DC. I don't know if that's how you did it, but
how is it equivalent?
Because triangle AFE is similar to triangle TBC. So basically, if FG over GE equals BD over DC, then angle FAG is angle BTD, so those would meet on the circle.
Yeah, I see. I didn't do it like that, but that makes sense also.
Okay, so you didn't need point P somewhere in the proof?
I needed that point. I'm not sure exactly what I did. I know that I used... Oh, actually, I remember. I think I remember now. I drew in the other midpoint of arc BC.
Oh,
So
so this one down
intersection of
here.
yeah. So intersection of AM with circles, circle.
Okay.
So that point, yeah. And obviously AM and U are collinear.
Yes.
And also ND and U are collinear. And now
Wait,
you can
how do you know
see,
that ND and U are collinear?
because we already proved that ND is the angle
The
bisector.
angle bisector. And we proved that, but in order to prove that, you have to use like spiral similarities, right? Like,
I used Treva's theorem actually.
oh really?
Yeah, just by using Treva's theorem, you can get that the BF over CE is BD over DC. Yeah,
Oh,
I guess you kind of need to use spiral similarities.
but then to show that BF over CE is NB over NC, eventually you do. Yeah.
Yeah,
Okay.
kind of is a spiral similarity, but yeah. And yeah, now you can see that GD and AU are parallel.
Yeah.
So you love to say Rime's theorem. I like to do the angle chase. But yeah, that proves by Rime's theorem that NGDS are cyclic.
Interesting.
And when you have that, you're done, basically.
Yeah, because that shows that NBSC is harmonic. Interesting. That's cool. Yeah, it's a nice problem. It's like generalizing Sharky Devil. You know, whenever you can generalize Sharky Devil, that's usually a good thing. All right, so the remaining problems, yeah, I don't know if they'll be easier or harder. Let's see. So we have trapezoid. I think some of them are